Welcome back. We are now on to lecture 23, properties of logarithms. So, before we get on to that, we need to recall some properties of exponents. Exponents and logs are closely tied together, so let's revisit some of this. Properties of exponents for b greater than 0 and real numbers u and v. B to the u times b to the v, that's going to be b to the u plus v. And next one, b to the u over b to the v is b to the u minus v. And last one, b to the u raised to the v is going to be b to the u times v. All right, everybody should be familiar with this, seen it in one shape or form before. Now we're going to look at the properties of logarithms. Somewhat similar. So logarithms are another way of talking about exponents. So each property of the exponents has a corresponding property of logarithms. So again, we still have the same things. B has to be greater than 0. B in this case has to be not equal to 1. And u and v are both positive real numbers again. Well, what we're going to have is log base b of u times v is going to be log base b of u plus log base b of v. I got into the other side. Oh well. Okay, so that's your multiplication rule, kind of. Well, product rule. Log base b of u over b, that's going to be log base b of u minus log base b of v. So your division turns into subtraction, multiplication turns into addition. Similar to what's happening here. Multiplication, we get addition. Division, we get subtraction. But it looks a little differently. And now, power rule here, we have that log base b of u to the v is equal to v times log base b of u. Okay. So let's show how one of these works. Let's show the product rule, the top one, first one. First, we're going to let x equal log base b of u, and we're going to let y equal log base b of v. Okay? So then we get that if we change this into an exponent, we get u is equal to b to the x, and v is equal to, change it into the exponent, b to the y. Okay? So what we have is log base b of u times v, right? That's going to be log base b of u is b to the x, v is b to the y, b to the x times b to the y. Yeah. All right. This now becomes an exponent rule that we know and love. This is log base b of b to the x plus y. Yeah. Log base b of b to some exponent. From last time, we know that this is just equal to x plus y, which is log base b of u plus log base b of v. So it works out. It checks out. We can do similar things for this rule and that rule, but we're good on that for now. If you want, try it as an exercise. So let's go on to some basic examples of what's going on. Log base 6 of 2 plus log base 6 of 18. Well, it goes the other way. So this is going to be log base 6 of 2 times 18, which is log base 6 of 36. 36 is 6 squared. So this is equal to 2. Okay. So I'm just going to write the product rule up here once more. Log base b of u plus log base b of v. Right. We don't always start here. Sometimes you have to go this way. Sometimes you have to start out with the addition and then move to the product. Right. It's an equal sign. So you can start on either side and change. Okay. So this guy, we have subtraction, the same base. So now this becomes log base 3 of division. So 567. So 567 divided by 7, which does simplify. So this is log base 3 of 81. Yeah. And so 81 is 3 to the 4th. So this is equal to 4. Okay. Next one. Log base 5 of 25. This is equal to 7 times log base 5 of 25. 25 is 5 squared, so this becomes 7 times 2, which is 14. Okay. So now, let's do the reverse of this one, sort of. We have negative 3 log base 9 to the of 27. Well, this is going to be log base 9 of 27 to the negative 1/3. Actually, I should have these parentheses on the outside. There we go. So it's log base 9 of 27 to the negative 1/3. So this is equal to log base 9 of 1/3, which is negative 1/2. Okay. Just logarithm properties going on here. Okay, log base 9 of 27. Well, I wrote the rule up here. So it's log of multiplication splits up into addition. So this does not equal, sorry, this is natural log. Natural log of 9 plus natural log of 27, right? It does not equal this. You can't take a log of addition and get the addition of logs out of it. That's not how the property works. So this would be bad. This guy just equals natural log of 36. Yeah. And that's as far as that goes. Okay. So on that same note of what you cannot do with logs, here are a list of things that aren't true. Are not true. The log base b of u plus v does not equal the log base b of u plus log base b of v, right? You can't take addition on the inside and make it an addition on the outside. That doesn't work. Same goes for subtraction. The log of whatever base of u minus v does not change into log base b of u minus log base b of v. Right? Another one, you can't take log base b of u plus v and turn it into multiplication. That's not how the property works either. Similar with division, you can't have division of logs and have log of the division of what you are taking logs of, right? Hopefully you can see that. So you can't have, 2 seconds, camera's gonna be weird for a second. Hopefully that's a bit better. You can't have log base b of u over log base b of v equal to log base b of u over v, right? That doesn't happen. And lastly, with exponents, the exponent has to be of what you're taking a log of. It can't be the log base b of u, all of that to the n, and then you bring it down. That can't happen. It has to be log base b of u to the n, right? The n has to be on the inside of the log. Then we're good. That's a B. It's a bad B, but whatever. All right. So logarithms can be tricky. You just got to make sure you know the correct properties and not do this. Not do any of these. These are bad. Okay. So let's work out some logarithms here. Properties of logs will let us expand things or contract things. So in this case, let us expand these expressions into more log terms. So start with this one. Log of xy over z, x times y over z, doesn't matter how you approach this first, I'm going to do it this way. This becomes log of xy minus log of z. Okay, so technically if you wanted to, you could have broken these two up first, but this is equal to log base x plus log base y minus log, not base, I shouldn't have been saying base this whole time, log of z. This is base 10, it's just regular old log. Log y, log x, log z. Okay, so our division turned into subtraction, our multiplication here turns into addition, and so we get 3 different logs. Okay, and that's as far as that will go. That we can not expand this anymore. All right, for this guy, well, there's a lot we can do. So this is x to the 4th times y to the negative 3 times z to the 1/2. It's the radical of z. So we can break this up into a whole bunch of addition things. Natural log of x to the 4th plus natural log of y to the negative 3 plus natural log of the square root of z. Okay? Natural log of x to the 4th, we can bring that 4 down. So we get 4 natural log of x. Same goes for this. We get minus 3 times natural log of y. And z, okay, this is the square root of z. You can't see that. This is not x. This is z to the 1/2. That's a z. It's a bad z, but it's still a z. So then this is plus 1/2 natural log of z. I'm not being set. There we go. So that is that expression fully worked out. It's not necessarily hard to expand or combine logs, but it takes time, and patience is definitely an exercise in patience sometimes. So this is expansion of logs. Let's go to combining logs. Right, 2 times log base 4 of x plus log base 4 of 3. Well, we're going to put the 2 back up in the exponent slot first. So this becomes log base 4 of x squared plus log base 4 of 3. Same bases, it's addition, so this turns into multiplication, and we get log base 4 of 3x squared. Okay, not too bad, not too bad. All right, next example. Natural log of x plus 3 plus 2 times natural log of x minus 7 times natural log of y minus 1/3 natural log of z. Okay, that's a little bit more. Well, let us put these coefficients back up in the exponent slot first. So this is natural log of x plus 3 plus natural log of x squared minus natural log of y to the 7th minus natural log of z to the 1/3. Yeah. Okay. So now let's put it all together. This is addition. These are subtractions. So what's going to happen? So I'm going to write one more line. So this is natural log of x plus 3 plus natural log of x squared minus, I'm going to pull a minus out from both of these. So this is natural log of y to the 7, that's a y, plus natural log of z to the 1/3. It doesn't look like a third, but it is. So it's this quantity minus that quantity. So these things are going to be on top, and this thing is going to be on the denominator. So we get natural log of addition turns into multiplication. So this is x squared times x plus 3 over, nope, huh, I made the mistake you're not supposed to make. Okay. Natural log of big thing, top and bottom. These are going to be on top. It's addition, so it turns into multiplication. X squared times x plus 3. And then on the bottom, we're going to have y to the 7 and z to the 1/3. You can say z to the 1/3 or cubed root of z. Either one works. Either one's fine. Okay. So contraction is not necessarily harder, but you definitely have to keep on your toes. Otherwise, you'll make a mistake like I almost did. Okay. So that's combining logs. Now, if you notice throughout combining logs and expanding logs, we had the same base, right? And that's what the properties are used for with logs that have the same base. So if we try and approximate a log value, okay, so question, give a decimal approximation for a natural log of 20. Answer is some weird number, right? 2.995, yada, yada. All right, now how about give a decimal approximation for log base 3 of 20? Well, a lot of calculators don't have log base 3 kind of a button. They always have a natural log and a common base 10 log, but not really anything special. So there is a way to get around this. And no, we're not out of luck in trying to determine a log if there's a different base than 10 or e. What we have instead is the change of base theorem. So we can change into any base that we'd like. So suppose that a, b, and u are real positive numbers. A is not equal to 1, b is not equal to 1. And then we get the following formula. Log base b of u is equal to log base a of u over log base a of b. So if we start out with log base b, we can change it to log base a and do that. So in particular, if we have log base b of u, we can change this into natural log of u over natural log of b. And that gets us into a natural log. Or we can change this into log of u over log of b. And we're in business again. These are the common logs that we want. So let's try re-expressing log base 7 of 11 using 3 different bases. Well, these two are nice and easy, so we'll get natural log of 11 over natural log of 7. We can use log, so this is log base, not 10, yeah, log base 10, so just log of 11 over log of 7, and pick your favorite base, log base 13 of 11 over log base 13 of 7, right? These are all different ways of rewriting log base 7 of 11, 3 different bases, still the same thing. So this guy, log base 3 of 20, that is equal to, if we change it to natural log, something that we have on our calculators and stuff, it becomes natural log of 20 over natural log of 3, which is approximately 2.727 stuff after that, right? So change of base theorem is very important, and it's kind of interesting how and why it works. This does look a little weird, right? But let's show how we get that. But why? Why does it work? Oh, let's show it. Let y equal log base b of a. Okay. So then from this, we get that b to the y is equal to a. right? Just change it into its exponential form. So now we want to take the natural log of both sides of this guy. So we get natural log of b to the y is equal to natural log of a. Okay. So this now becomes y times natural log of b equals natural log of a. Let's keep solving for y here. Y is equal to natural log of a over, that's an a, natural log of b. And remember or recall, whatever, since y is equal to log base b of a, we get, well, y is equal to log base b of a, so we get log base b of a is equal to natural log of a over natural log of b. Okay. We didn't have to take the natural log. We could have taken the regular log. We could have taken log base 3, log base 4, log base Fred, so long as it's positive and not equal to 1, right? It doesn't matter, but this is a nice, quick, easy way of showing that change of base theorem works. It looks weird, but it works. Okay. So now let's do a few examples of change of base examples. So log base 5 of e is approximately 0.621. Estimate the value of natural log of 625. Okay. Well, we're given natural log base 5, not natural log base. Sorry, that was so wrong. We're given that log base 5 of e is something, right? So we would want to use that base in our change of base. So we want to find out what natural log of 625 is. Well, let's change it to log base 5. So this becomes log base 5 of 625 over log base 5 of e, because the base of a natural log is e. And this is equal to 4 over 621, 0.621, right? Log base 5 of e is approximately this. And 5 to the 4th gives us 625. And this, not equals, this is actually approximately, what, 6.44. Right. So that's one approximation where we use change of base. So now let's look at this example and try and solve for x. And in the process, we're going to have to do some change of base because we have log base 5 over here and log base 25. Usually, if we're trying to solve something like this, if they're the same base, then we can just equate both sides, which would be nice. Well, let's go for that. So let us change this guy, log base 25 of 4x plus 16, into something log base 5. Right. So we have log base 5 of x plus 1. That's equal to, now if we change this into log base 5, this becomes log base 5 of 4x plus 16 over log base 5 of 25. Okay. So now this is log base 5 of x plus 1. Log base 5 of 25 is just 2. So this becomes log base 5 of 4x plus 16 all over 2. Okay, let's keep going. Let's move the 2 to the other side. So we get 2 times log base 5 x plus 1 log base 5 of 4x plus 16. All right, again, we still want log base something equals the same log base something. So we have log base 5, log base 5. This 2 we got to get rid of. So let's put it back up in the exponent slot here. Use properties of logs. So we have log base 5 of x plus 1 squared, right, equals log base 5 of 4x plus 16. Okay, log base 5 of something equals log base 5 of something else. So that means that we have x plus 1 squared is equal to 4x plus 16. I'm running out of room, so I need to write this down. Okay. So from this, we're going to get, so now we just have to solve for x, right? So this becomes x squared plus 2x plus 1 equals 4x plus 16. This gives us x squared minus 2x minus 15 is equal to 0. Move that over, yeah. Okay, so yeah, this factors into x minus 5 times x plus 3 equals 0. So x equals 5 or x equals -3 as our possible solutions, right? Well, there's a problem here, because where did we start? We started, I'll move back, but we started with log base 5 of x plus 1 and log base 25 of that thing. If we plug in x equals -3 into here, we get something bad, right? We get log base 5 of a negative number, which we can't have, right? That's not defined because the domain of a logarithm is all positive numbers. So this can't be a solution. So we only have one solution, because log base 5 of -3 plus 1 is bad, right? Because log has domain 0 to infinity. Log or log base, whatever, doesn't really matter. Okay. So x equals 5 is our solution for this guy. All right. Now, let's find some inverses using logarithms. Okay. So find the inverse of the function g of x is equal to 3 times 7 to the x minus 5 and express it in terms of the natural logarithm. Okay. Well, we've done inverses before. We're going to let y equal 3 times 7 to the x minus 5. We're going to swap variables. Swap x and y, and we're going to get x equals 3 times y, or sorry, 7 to the y minus 5. And we're going to solve for y. So we get x plus 5 is equal to 3 times 7 to the y. X plus 5 over 3 is equal to 7 to the y. We take natural logs of both sides. Yeah, we do that. And we get, well, so here's the thing. You can take natural logs right off the start, but we're going to do log base 7. So you can do two things. One, log base 7 of 7 to the y equals log base 7 of x plus 5. It's a 5 over 3. And so this gives us y is equal to log base 7 of x plus 5 over 3. We want this in terms of the natural log, so we would have to use change of base on this. And so this becomes y is equal to natural log of this guy, x plus 5 over 3, divided by natural log of 7. And that's your inverse to g of x. This is g inverse of x. Now, the other thing you could do, like from here, we can go one way or we can go this way. And it's basically take the natural log right off the bat. And so you would have natural log x plus 5 over 3 equals natural log of 7 to the y. The y still comes down. And so you would have y times natural log of 7. And then you would divide the natural log of 7 over. And you get to the same result. But since we have been talking about change of base and stuff, it's good to go through it as another example. Anyway, we found g inverse of x in terms of the natural log. So why do we care so much about logarithms? They're very useful. They're very useful in solving equations, taking measurements, and performing calculations. We'll get to a fun little historical note at the end here, which is very soon. So, solving equations, we've already done all that. Let's look at taking measurements and stuff. This is mainly just some fun stuff, but quantities that have large range of possible values are sometimes best measured using a logarithm scale. For instance, sound and the decibel scale is very useful. As you can see, decibel level equals stuff involving a log, I's intensity of the sound measured in units. W, I want to say that's watts per meter squared, but that doesn't sound quite right to me. So decibel scale, I's intensity measured in the appropriate units. Another good example for measurements is space travel, and I'm not going to try and pronounce that, someone's rocket equation. Delta V is equal to V sub E, natural log of m naught over m sub f, where we have V sub E is the velocity, m sub O is or m naught is the mass of the vessel, and m sub f is the vessel without fuel. All this is just for fun, really, and just showing you how useful these actually are. Another thing, so other than measurements, there was also performing calculations. So logarithms were developed actually as a way to make multiplication easier, right? Because remember our product rule, we have log of AB is equal to log of A plus log of B, right? So if we wanted to try and multiply these two big, ridiculous numbers, that would take some time. But if we consider this to be A and this to be B, then log of AB is going to be log of A plus log of B, yeah? Now, log of A, log of B, this is equal to 4.21442 plus 9.78558 numbers. Now this, add these two things up, adding is a lot easier than multiplication half the time. This is equal to 14, roughly, log of A, B. Or is it directly? No, that's actually equal to 14. That's a 2, 1 carries over. Yeah, that's equal to 14 solid. And so this, we take the log of AB equals 14, change that into an exponential, and we get 10 to the 14 equals A times B, which is 1 and 14 zeros. Too many zeros. Anyway, it's a lot easier to, instead of just multiplying this nonsense out, figure out the logs and get some sort of smaller addition and then take an exponent. There is a question of how do they know what the heck the log is of 16,384? Well, that's a very good question. And what they used to have were log books, literal books of that were just tables of logs, and it was log base 10 of a bunch of numbers, and people calculated them by hand. And it's an interesting bit of history if you're actually interested. Another thing on still historical stuff and importance of logs and making calculations, making/performing calculations, was making them sort of linear. And so they changed multiplication. You would change multiplication into addition, and we convert from two-dimensional operation to a one-dimensional one. So this one rule is very important, and it allowed mathematicians of the 1700s to invent the most powerful computing devices until the creation of electronic computers. And that was, in fact, slide rule. I actually have one or two. They are very fun to use and very interesting if you want to look them up on your own. And there's a whole way of calculating exactly log base A, log base B using a slide ruler. And it's very hard to give good examples like this while not in person because slide rulers are cool. But anyway, this is the end of the historical note, and well, we finished the material for this chapter a while ago, or lecture, sorry. So until next time.